Pig iron contain about 4% carbon and small amounts of sulfur, phosphorus, silicon and manganese as impurities. Now another variety called cast iron, CAST-IRON, cast iron. It contains only 3% carbon and it is made by melting pig iron with scrap iron and coke using air blast. Scrap iron means iron waste, iron in the form of waste. SCRAP, scrap iron, waste iron. Now pig iron is melted with the scrap iron and coke, that is carbon, using air blast. Now some amount of iron is oxidized as ferrous oxide, which will react with the carbon, forming carbon monoxide and iron. So that carbon is removed as carbon monoxide gas. So a reduction in the percentage of carbon occurs. Now sulfur, phosphorus, silicon and manganese are not affected appreciably. Then the most pure form of iron, that is wrought iron, WROUGHT, wrought iron, WROUGHT, wrought iron. It is the purest form of iron, containing no carbon at all. Now for this, cast iron is taken in a reverberatory furnace, and the furnace, inside the furnace there is a lining of hematite, that is iron oxide, and heated in this furnace. Hematite oxidizes carbon to carbon monoxide, so that hematite is iron oxide Fe2O3. It oxidizes carbon to carbon monoxide and thereby itself getting reduced to iron. So an equation is Fe2O3 plus 3C giving 2Fe plus 3Co. Now limestone, that is calcium carbonate, it acts as a flux, and sulfur, silicon and phosphorus are oxidized to their oxide, sulfur dioxide or sulfur trioxide, silicon dioxide, phosphorus pentoxide. Now calcium oxide combines with sulfur trioxide, CaO plus SO3 giving CaSO4. So that may be considered as a slag. Similarly, CaSiO3 and Ca3PO4 twice, that is Ca3PO4 twice, that is calcium phosphate. So all these are slags which may be removed. So the impurities sulfur, phosphorus, silicon and manganese present in cast iron or pig iron is removed as slag, and for that we use a reverberatory furnace lined inside with hematite. Hematite oxidizes carbon to carbon monoxide. Then there is supply of air, so that the oxides of sulfur, silicon and phosphorus are formed, and these oxides combine with limestone iodide to produce the corresponding slags, calcium sulfate, calcium phosphate and calcium silicate. These are removed. So we get almost pure iron. It is called wrought iron. Now coming to the extraction of copper. Now the usual ore used is copper pyrites, and we know this compound is, this ore is concentrated by flotation method, and again it is calcined and roasted, and after calcination and roasting, this ore is mixed with the silica and heated in a reverberatory furnace. Reverberatory furnace, a particular type of furnace. Now ferrous oxide formed will react with the silicon dioxide forming slag. Ferrous oxide may be formed during roasting, and again the ore itself will react with the air, producing copper sulfide, ferrous oxide and sulfur dioxide. Now that ferrous oxide combines with the silica, producing ferrosilicate. Now here ferrous oxide is basic oxide, so it is the gongs, and silicon dioxide is the flux, and this is the slag. Now copper sulfide will react with air, producing cuprous oxide, and this reaction is partial, in the sense only a part of cuprous sulfide will get oxidized to cuprous oxide. Then this cuprous oxide formed will react with the cuprous sulfide, producing copper and sulfur dioxide. So you have the equation Cu2s plus 2Cu2O giving 6Cu plus SO2. Now copper produced in this manner will contain dissolved copper sulfide and ferrous sulfide as impurities. Now this combined mixture of copper sulfide and ferrous sulfide is called matte, M-A-T-T-E, copper matte it is called. So it is an impure form of copper. Now this matte can be further purified using a furnace. Now matte is charged into a furnace lined inside with silica. So the furnace will be lined inside with silica, that is SiO2, and a little silica is added also along with the matte. So matte is charged into a furnace lined inside with the silica, and some silica is also added, and a hot air blast is blown. So we have matte which contain copper sulfide and ferrous sulfide, and the furnace is lined with the silicon dioxide, and that will be acting as the flux, and some silica is also added, and a hot air blast. The air blast converts ferrous sulfide to ferrous oxide, and the ferrous oxide will combine with the silicon dioxide in the added charge as well as the lining to form ferrosilicate, and its slag may be separated. Now the reactions which occurred previously, that is copper sulfide plus 3O2 giving cuprous oxide and sulfur dioxide, cuprous oxide and cuprous sulfide giving copper and sulfur dioxide, repeat here also. Now we get almost pure copper. Now this melted copper on solidification, bubbles of sulfur dioxide gas will escape from the solid copper. So we will get holes first, and these holes will form what is called blisters. Now such a blistered appearance of the surface of solidified copper is due to the escape of sulfur dioxide gas from the molten copper, and that copper obtained, impure copper obtained, will be called blister copper. Now almost pure copper is made by electrolysis, electrolytic refining it is called. Now in electrolytic refining, generally the impure metal is made anode and a thin sheet of pure metal is made cathode, and a proper salt solution of the metal is made the electrolyte. Now here we take impure copper as the anode and a thin sheet of pure copper as the cathode, and then copper sulfate solution as the electrolyte. So we have impure copper as thick blocks as the anode and a thin sheet of copper acting as the cathode, and copper sulfate slightly acidified to increase its conductivity. So CuSO4 plus acid. Acidified copper sulfate is the electrolyte used. At the anode, copper dissolves to form cupric ions and electrons, and at the cathode, cupric ions are reacting with electron to form copper, so that this cathode becomes thicker and thicker as the reaction proceeds, electrolysis proceeds, and the anode becomes thinner and thinner, and the impurities present in this anode will be accumulating below this anode as a heap, and that is called anode mud. Now this anode mud contains elements like antimony, selenium, tellurium, and also costly metals like silver and gold, and platinum is there. So these are costly metals, silver, gold and platinum. So recovery of these metals, these costly metals, meet the cost of refining. So anode mud is useful in meeting the expense of refining. Now zinc is also refined in this way, that is electrolytic refining. Now metallurgy of aluminum, that is from bauxite, we have seen that bauxite is purified by leaching process. That is, bauxite is leached with the concentrated sodium hydroxide solution. The impurities present are mainly silica and titanium dioxide. Now silica and alumina, Al2O3, dissolves in sodium hydroxide, producing sodium silicate and sodium aluminate. Now carbon dioxide is passed, hydrated aluminum oxide is formed. With strong heating we get Al2O3, that is alumina. Now for electrolysis, alumina is a high melting compound, so a salt is added, that is cryolite Na3AlF6. It's a combination of 3NaF and AlF3, or better we can use calcium fluoride. Now this added compound, electrolyte, will lower the melting point of aluminum oxide and also make the solution conducting. So two purposes: lower the melting point and make the solution conducting. Now steel vessel lined with inside with the carbon, maybe in the form of graphite, act as the cathode, and rods of carbon immersed in the electrolyte act as anode. So there will be a steel vessel, there will be an opening here, and the vessel is coated inside with carbon. So this is carbon, and that is acting as the cathode, and then the electrolyte is there, which is alumina, and cryolite mixture, and we dip carbon rods into this electrolyte, and they act as the anode. Now alumina decomposes into aluminum and oxygen. Now due to the high temperature prevailing in the electrolytic apparatus, the oxygen which is liberated at the anode, because oxygen has O2 negative, will go to anode and give out electrons, okay, to the anode. So oxygen liberated at the anode will react with the carbon, because we are using carbon anodes, and will form carbon monoxide and carbon dioxide. So anode is burned away as gaseous product, so that the contact with the electrolyte is lost. So we have to dip continuously the carbon rods so that the contact is retained. And when the electrodes are completely exhausted away as carbon dioxide and carbon monoxide, we have to use fresh set of carbon rods as anodes. Now the overall reaction is written as Al2O3 giving QAl plus CO2, and I said oxygen liberated at the cathode will decompose it away as carbon monoxide and carbon dioxide, and a detailed reaction may be written as at the cathode Al3 positive plus 3 electron giving Al, at anode C plus O2 negative giving CO, and C plus 2 O2 negative giving CO2. Now copper forms copper from low grade ores. Now what is done is the low grade ore in the form of a heap. So this is low grade ore is soaked with dilute sulfuric acid, or they use bacteria. Now the copper part will dissolve in dilute sulfuric acid, and the copper sulfate will be formed, and it is reduced using hydrogen. So that Cu2 positive plus 2H giving Cu plus 2H positive, or better we can use iron, Cu2 positive plus Fe giving Cu plus Fe2 positive. So copper plus sulfuric acid giving copper sulfate and hydrogen. Now impure copper, that is low grade ore, is soaked with the dilute sulfuric acid, or we can use bacteria. Now copper sulfate formed is collected and reacted with iron or hydrogen as the reducing agent to get copper. Now coming to methods of refining. Now the simplest method, that is distillation, is used for low boiling metals like zinc and mercury. Now what is done is the mixture is boiled. Mercury is having low boiling point, zinc is having a boiling point nearly 900 degrees Celsius. Mercury is also a low boiling liquid. Now the vapors of these metals are cooled and collected. So zinc and mercury are refined by distillation method. Now there is another process called liquefaction. See, the impure metal is placed at the top of a sloping furnace. It is heated. Then the low melting metal will come down as a liquid. Now lead and tin are purified, refined by liquefaction process. Now there is argentiferous lead. Argentiferous lead. It is lead containing silver argentum as the impurity. Now, during liquefaction, silver will be deposited as a solid and lead will flow as a liquid. So, that method is advantageous because we are getting a costly metal like silver. Now, electrolytic refining, we have seen the case of copper. There is another method which is most important in the production of semiconductors, and this method is called the zone refining. Now the material, metal or a non-metal, silicon is a non-metal, and germanium, it's a semi-metal metalloid. So the material, the element in the form of a rod is heated at one end using a coil. Now this zone is melted. Now there is a principle that impurities preferentially dissolve in a molten metal than in the solid metal. So that when this zone or region is melted, the impurities will pass into the melt from the solid state. Now this coil is moved along this rod, then this melting process is repeated, and the dissolution of impurities in the melted zone is repeated till we reach the other end. So that the other end, when the coil is there, will be in the molten state, and that will contain a major portion of the impurities. Now the coil is removed, and this region is zone is solidified. Isodoine is zone. Now this process is repeated several times till you get all the impurities here, and this portion is cut off to get the pure metal or a pure material. Now I told you earlier that materials used for preparing semiconductors, for example germanium, silicon, boron, gallium and indium, are purified by this method. Now vapor phase refining. Now here the policy is that the metal alone will form a volatile compound with a reagent at low temperature, which will decompose to the pure metal at high temperature. Now there are two processes called Mons process, where nickel is purified by Mons process at 330 to 350 Kelvin. Nickel reacts with carbon monoxide and we get NiCO4 times nickel tetracarbonyl. It's a volatile compound, and this nickel tetracarbonyl is decomposed at high temperature 450 to 470 Kelvin to nickel and carbon monoxide. Now this carbon monoxide may be recycled to the impure nickel, and the process may be repeated. Now this is Mons process used for the refining of nickel, and there is another method called the Van Arkel method, Van Arkel method. Now the crude, here also the method is similar. The crude metal is heated with a reagent which will form a volatile compound which is decomposed to the pure metal at a high temperature. The principle is the same. Now this method is used for the purification, refining of metals like titanium and zirconium, which will contain dissolved oxygen and nitrogen. Now in an evacuated vessel, the metals titanium or zirconium is reacted with iodine. Zirconium tetraiodide is formed, which is volatile, and it will reach a tungsten filament heated electrically at a high temperature, kept at a high temperature, so that zirconium tetraiodide will decompose to zirconium and iodine, and the zirconium will be deposited over this tungsten wire, and iodine vapor will be collected and then recycled. So the reactions are Zr plus 2I2 giving ZrI4, then ZrI4 giving Zr plus 2I2. So that is Van Arkel method. So Mond's process for refining of nickel, and Van Arkel method for refining of zirconium and titanium. And there is chromatographic methods also used for refining, that will be discussed later. Thanks for listening me.